Well, I had the opportunity to give a detailed introduction to today's speaker yesterday. I'll shorten it up, but I did want to take the opportunity to actually describe our guest's titles. Maxwell Bennett is the University Chair Professor of Neuroscience in the Department of Physiology and the Scientific Director of the Brain and Mind Research Institute at the University of Sydney in Australia. He has, for those of you who weren't here yesterday to hear the more detailed description, he has an illustrious career in neuroscience, particularly pioneering ATP and non-cholinergic synapses in the autonomic nervous system. Has worked on many aspects of neuroscience, and now at his institute is able to supervise and be part of an enviously diverse neuroscience research program in all areas of neuroscience, from the pure experimental to the population level and applied psychology. And so it's a great pleasure to introduce Max Bennett.
Thanks, Ken. Yesterday I opened up by pointing out, of course, that we have a corporeal body and a range of psychological capacities: remembering, feeling, perceiving and thinking. And then I took the story back to its basic roots, going back 3000 BC, and indicated to you the way in which the Egyptians had developed a concept of what it means to be human in terms of a tripartite concept which had rationality, it had in the second part the emotions, and in the third part it had things to do with the vegetative state, nutrition, the need for energy. And then I developed that story and showed you by means of this table here the way in which it had been taken up by successive generations over around about 4,000 years. The way it had been taken up in the 8th century by Homer, developed by Plato, who still has such an enormous effect on the concepts developed in this area in the Western world, by the genius Aristotle, and then I left out of the equation the person whose shadow we definitely work under at present, Descartes. Because as you can see by the table, Descartes made a very big change because he confiscated all of this. This story, this tripartite story here, very clear, he confiscated it and brought it down to this concept of consciousness. And he's defined consciousness of everything that you experience within you, like the stream of consciousness of Virginia Woolf, who I've been writing on lately. Thought, which was related to the nous, the mind, he regarded as a special kind of attribute of the soul, as he was thinking of in these terms. But consciousness implied that we had not only thought, which was buried in consciousness, but the capacity for perception, for feelings, emotions. They were capacities that belonged to the body and were open to physiological investigation. They weren't something of an ephemeral nature at all. They were mechanistic things which nevertheless the mind, or in particular consciousness, had the capacity to make contact with. So we have thought, which was a special category, not belonging to the corporeal, but these other aspects, which had been divided into nutritive and sensitive and what have you, these other aspects were aspects of the body undergoing the capacity for mechanistic analysis, which really created the subject of physiology. So, if that's the case, how did he conceive of consciousness itself? How do we break that down? And my colleague Peter Hacker and I looked at this a little bit recently, and what he did really was say, well, look, when it comes to things like memory, this is open to straight mechanistic analysis, physiology if you like. It's a consciousness of facts. You're ruminating on facts of one kind or another, you're remembering these facts. Or, for example, much more perhaps easily to be grasped, is you have perceptual consciousness. I'm aware now that Gary is not taking any notice of me but is writing in his book. Okay, so my perception is caught by the fact that out of the side of my visual field his hand was moving, and so I become conscious of that. And so on and so forth. Emotions, conscious of the fact that I'm a little stressed now in having such an audience in front of me to take in what I'm trying to say here. So there are these various kinds of aspects of consciousness, our awareness being caught by different kinds of activities which spelt out by these little clouds here. However, what Peter and I did in our book, which is now 13 years old, Philosophical Foundations of Neuroscience, was we bundled these things together and said that really you can consider them the way that emerged in the 19th century as a form of what we call intransitive consciousness. That is, are you conscious at all or are you unconscious? Have you been hit by a car? Have you had an anaesthetic? Are you asleep? In which case you're unconscious. So if you're unconscious, then clearly none of these capacities are active at all. You're not conscious of Gary's hand moving, you're asleep. So none of that is actually occurring at all. Well, the question then of whether you're becoming conscious or not, unconscious, whether you have these specific levels of consciousness, is something which actually developed historically in a rather intriguing fashion. Because at the beginning of the 17th century, when Descartes was just getting going, there was no such word in the English language. The word consciousness does not appear in Shakespeare whatsoever. So where did it come from? Well, it comes, of course, from the Latin, scius, I know, and cum, with, so giving us the verb conscicio. It comes from that, but it wasn't in the English language at all. And when it gradually crept into the English language around about the middle of the 17th century, it came to mean that I have some special kind of knowledge, or information if you like, which I am privy to, and so is a special friend of mine privy to. We are the only ones who have this knowledge. And then it gradually evolved towards the end of the 17th century in English and into the 18th century to something which I am privy to alone. No one else knows about this. And then it evolved further by around about 1750. It evolved to mean I am aware of the information or of the kinds of experiences I've had which are privy to me in a very personal way, which is pretty much the way we say now that you're unconscious because you're still under the anaesthetic, or you are conscious, that sort of thing. However, the word being unconscious or being conscious didn't actually occur in English until about 1850. So you couldn't be unconscious if you were a Brit until around about 1850, because the word didn't exist to describe that. So I'm going to take that word, though, the way we now use it, of course, unconscious, not capable of any of these capacities at all, and I'm going to elaborate for you the way it has been thought of in terms of the relationship between the corporeal activities, that's the activities of your body, and whether you are conscious or unconscious. Some of you will be very disappointed that I'm not going to spend some time on this one or that one. Well, these are lectures, or shall I say presentations, on their own. But let's deal with this very interesting one, to say the least, of whether you are conscious or unconscious at all. Now, for Descartes, it was very straightforward, of course. The whole matter was that you were conscious or unconscious, depending on the relationship between this bit of corporeal, as I mentioned yesterday, the pineal gland, and the spiritus substance in the ventricles, where all those wonderful things happened that allowed you to enter the mind itself. And these, as you know, and I rather love these, so I'm going to mention them again, these little wiggles here represent what Aristotle said was impossible. That is, you cannot have the corporeal interacting with the spiritus by having little wiggles. There has to be some bridging process, and you can't bridge two such unlike substances. Or, my favourite philosopher, Spinoza, would say, it's impossible to bridge them. They must go together hand in parallel, but there can be no causal relationship between them at all. Now, we got rid of that very easily because while Descartes was still alive, it was shown that the pineal gland isn't there at all. The pineal gland is actually hanging outside the ventricles, and therefore the whole game collapsed. However, it hasn't collapsed as far as more recent investigations are concerning whether you're conscious or unconscious and what's going on in the body, in the corporeal. So we go now to a diagram which I used a couple of times yesterday. And this is the diagram which really goes back to the Silman lectures of Sherrington in Yale around about 1906, 1907. And I mentioned to you that at that stage that we knew a lot about this part of the brain here concerned with hearing, a lot about this part of the brain here concerned with vision, here with being able to move your limbs, and here being able to experience whether you've got an itchy skin or whether your hand is up here somewhere, that kind of sensory information. And then I went on to show you that when we come to very, shall I say, simple cognitive things like distinguishing between whether there's numerals on that wall over there or whether in fact there's alphabet on their wall over there, then we start engaging this large area that Sherrington knew nothing about at all, these areas here. We start to engage those in quite a complex way. That is, there isn't a module here related to you distinguishing between numerals and the alphabet. It's distributed all over the place, this sort of activity. And I finished on a rather sour note by saying I found it all rather disappointing because as a consequence of that distributed activity and the lack of modularity there, we have no grip. We have no synoptic view of where we're going in research on the corporeal in relationship to our capacities or in relationship to whether we're conscious or unconscious. Well, I'm going to invert that in this presentation. I don't want to be kicked out of Yale. I'd rather be someone who's thought of in a reasonably kind way. So I'm going to actually take up the story now and show you that we are now, I think, in a region of investigation on the brain, which I'm very glad, as I said to Bob earlier this morning, I'm very glad to be alive to actually see it going on. What is going on in all this grey matter here is something I touched on before, namely that there's lots of things called neurons in there. And what we're going to inquire into is what are the neurons doing when you become unconscious? Now, what is the relationship between the corporeal neurons and the capacity to be conscious or unconscious? We're going to stick to that level of investigation throughout my presentation. Well, of course, as I said last time to you, and some of you will be bored with this because you've already seen it, we have these neurons here making up the cortex, the mantle of the cortex here, and they connect with each other via these little junctions here, the synapse, one there, and there's about 10 raised to the power 15 of these, for those of you who like those sorts of numbers. And one part of the cortex, which might have these neurons in it, can connect to another part of the cortex, which is a long way away. So from there all the way to there. You connect via these processes, the axons of the neurons, projecting in the white matter, which I showed you yesterday, goes for a long way, and then they come back into the grey matter again and connect up. So we've got long-range connections going all over the place. And our inquiry is, what's going on here when you become unconscious? Now, I'm now going to develop a theme to embarrass my host, Bob Schulman, and show you that one of the two major ways of coming to grips with this in a way which I think is very exciting. It gives us an overview of our subject. It leads us down paths which the next generation will certainly have a lot of fun following up. And if I have anything to do with it, I will also have a lot of fun following it up. And that is, we can now measure the activity in a region of this, like this here. We can now measure it quantitatively with great accuracy. Now, I'm not talking about what's going on here. I'm talking about this part of the brain here, what's going on, versus, say, that part of the brain when you become unconscious. And the way it works out is by means of this little diagram, which will throw some of you off your seats. Here. This here shows you one of those synapses. So this is about 1/1000th of a millimetre across here, and it's making a connection onto another neuron here, another 1/1000th of a millimetre, and there's a third little bit there. This is the neuron cell body, which is about 1/20th of a millimetre, and it sends out its axon running around here like this, and then it ends up making one of these little synapses. And I've just increased the magnification here and blown it up here to blow you out of your seats with all this colour and things going on. So what did Schulman and his colleagues, his wonderful colleagues Doug and for me, do? Well, what they've shown over the last quite a few years now is that you can measure the actual electrical activity here, not by putting electrodes and all those fancy things in there, but by going at it this way. There's lots of electrical activity associated with the workings of these things here. And when there's electrical activity, there's movements of particles from in the extracellular space here into the neuron. Now, the neuron can only take so many of these particles, which are called ions, before it'll cease to work. I mean, it just gets loaded down. So you've got to get them out. You've got to get them out. Otherwise, the whole system will just collapse. In order to get them out, you have to have pumps. So there's little pumps all over the place getting these ions out. In order to get pumping going, you have to have energy. You have to have some form to drive the pumps, just the same as a mechanical pump out the road there. You've got to have, in the form of petroleum or something like that, some form of energy. So what happened in the laboratories here in Yale was to develop a technique for measuring this energy that's actually been developed. It's very simple, actually, the technique. I hate to offend my host, but I think it's reasonably simple. So if you can measure this energy, you're actually getting a measure of all the electrical activity. Therefore, if you're becoming unconscious, what happens to all this activity can be given a very, I think, quantitative measure by looking at this energy without doing all this fancy electrical stuff. And what you get is one of the two most informative diagrams, I think, that's floating around at present in trying to relate the corporeal to consciousness or unconsciousness. And I'm afraid it's a graph again. And it shows you this. Now, I'm going to take you slowly through this because I think it's a Bobby Dazzler. Here, on the vertical axis here, I have the amount of energy, if you like, in a particular part of the brain. And what I'm showing you here is that up here you've got normal wakefulness. So you've got all the activity in the brain's going on and churning away. And so we'll just call that the 100% energy level, if you like. As you go to sleep, normal sleep, this energy level drops. Bit by bit it drops until you get down to a level which is about 50%. So down here, when you're fully asleep, what we call slow wave sleep, down here, when you are unconscious, half of your brain activity is still going, flat out. So you've still got 50% of your brain working when you're fully unconscious. If you want to have another angle on this and you take a general anaesthetic, then the same thing happens. You take the general anaesthetic and you gradually see the amount of energy being utilised by the brain drop and drop and drop until it gets to about 50%. And then all this continues going here. So that's very interesting because it's during this drop here, as you become unconscious, that the electroactivity is falling out. Also, if you look at behaviour here, that is, what does it mean to become unconscious? It's very revealing because, as any anaesthetist will tell you, what is happening is, first of all, your speech becomes blurred. You don't start to talk very clearly at all. Secondly, you can't respond to a request. The audition starts to get fouled up. Thirdly, if you're pinched, you stop moving your arm away straight away from the site of the pain as a consequence of the pinch. So all these things, volition, perception, matters of that kind, giving a thoughtful response to a request or a question, all starts to become blurred. And they don't come all blurred at the one time. Some you start to lose before others of these different capacities. So if you follow those down, as you lose this until you've fully lost all these capacities and you're unconscious, that is a very interesting insight into what's going on in the brain as you become unconscious. So the big question is there certain areas of the brain which are critical in terms of dropping their activity down like this for you to become unconscious, whereas other parts of the brain don't drop down at all? Is there any particular parts of the brain? Those parts of the brain would be Descartes' pineal gland. We would at last solve the problem because here we have the part of the brain, the corporeal, which when it becomes relatively inactive, we become unconscious. So this is the magic little bit. We want a corner. So there's one kind of interesting kind of angle there. The next kind of angle, which is of great interest, is what is going on here. Now, I reckon that the next generation, including me, of course, will work out what's going on here along the lines that I just indicated. But what's going on here is something which might interest someone who's completely wrapped up in Freudian analysis. I mean, this is the true subconscious down here, and we haven't got a clue really what's going on. Certainly memory is going on. If you look in parts of the brain responsible for you remembering things, then what we can see during this period here, that those parts of the brain are very active. In fact, they're active in ways which can be fairly precisely delineated as associated with you remembering some event when you were awake. So that is certainly going on, but that's a very small part of the total activity which is still going on in this period here. So I'll leave you with this delectable Freudian area here, which no doubt, well, some people are already having a go at it, but it's so abominably vague that I won't bother you with telling you about it. Up here, you'll notice that this line here is not sitting on 1. It's sitting a little bit different to 1, a little bit more. And that's because when you are fully awake, you don't have a set amount of activity all over your brain. The activity in the brain is actually varying a bit all the time, up and down here. Not very much. The average is about this, but it's varying up and down by about 10%. That's going to be important in a moment. I mean, what's going on with all this variation when we're fully awake? So I think you can see that this diagram opens up a whole range of activities which are quantitatively capable of being analysed in terms of what is going on with the activity of the brain and which parts of the brain as you lose consciousness. And of course, if you want to go that far, what is going on in the context of being in the subconscious, in the id, if you like, what's going on there. Now I'm going to leave that hanging there for a moment because I'm now going to come from this problem of when you become unconscious from a slightly different angle. An angle which we looked at to some extent yesterday. And it's this. All right, if we can look at different parts of the brain, now we've coloured them in here in different ways and we've given them different numbers. And if we look at the change in energy, the previous diagram, we might find this part of the brain here is losing that energy as you become, or that activity if you like, as you become unconscious, whereas this part here is not very much. Well, as I said earlier, that would be very interesting. And this is looking at the side of the brain here. This is looking in the middle of the brain here. That's a section down the middle there. And we can look at all these different areas in that way. But one of the most interesting way of looking at the areas is using the technique which Sherrington first described here at Yale 100 years ago. And it's the technique I introduced you to last time, the upturned flask technique, where what Sherrington did, just to remind you, was he exposed the brain here of a chimp and put this upturned flask full of fluid on top of the exposed cortex there, and he reasoned that, just as the Schulman group have shown now, that if in fact the neurons are very active just here, then they'll need more energy. They'll need glucose, for example, and oxygen, the energy providing elements, which can only be provided by the bloodstream. So if the bloodstream increases here, increase in blood volume and blood flow here, it would indicate that the neurons here were very active because they needed that energy, that glucose, that oxygen. And therefore, if the diameter of the blood vessels increases, there'll be the volume here will go up, the fluid level here will rise, indicating that the blood vessels are becoming engorged with blood to supply this energy. And this is the famous technique which he developed and which is now called functional magnetic resonance imaging. So my question is, if we apply that flask there at the back of the brain, and at the same time we take another flask and we put it up here at the front of the brain, what kind of fluctuations are they seeing? Because I showed you before that there's fluctuations going on all the time in the activity of the brain. Well, these are the sort of fluctuations that they see when you do that experiment. Here are the fluctuations. This is time here, and up here, if you like, is energy or whatever else you like. And here in yellow is the front of the brain, and here in blue is the back of the brain, and here in black is an intermediate area. Now, you might say, oh, well, that's jolly good. What's all that mean? Well, what it reflects is that, as I said to you, about 10% of the activity of the brain all the time is fluctuating up and down. These profiles here are measures of that fluctuation. So this is the front of the brain fluctuating, there's the back of the brain fluctuating, the middle of the brain fluctuating there. Now, the extraordinary thing is, I'm not going to bore you by taking you through all this very carefully, but if you look at that, you'll find that in some cases, those fluctuations are in phase with each other. That is, they can be correlated. That's the extraordinary thing is that something up here is actually increasing its activity in line with, that is, in the same phase with activity at the back here, miles away as far as cortical projections are concerned. So we've got the back of the brain now, in this example, going along, correlated in its activity with the front of the brain. Now that's very interesting. And that really implies that there's some kind of activity going on which binds the front and the back of the brain together. Now this is not someone who's doing anything. The person who's got these flasks, one up the front and one up the back here doing these measurements, is not reading Shakespeare. They're not mowing the lawns. They're just sitting down, doing nothing in particular. That is, they're caught in Virginia Woolf's stream of consciousness, if you like. They're not doing anything particular. And yet these correlations are occurring between different parts of the brain, and they're reasonably recapitulated from one time to another and from one patient or one subject to another. That is, this part here is correlated with that part, and contrary to that, this part over here is correlated to this part here. So there are these kinds of activities going on altogether. And you might say, well, so what? So what? Well, the so what part is, first of all, how could this occur? And I told you last time, that is yesterday, how it can occur. And it can occur because of the other great, I think, type of technique that's come available in the last several years. And this is a magnetic resonance imaging technique, which I won't go into, but it allows us to see the white matter tracts of the brain. That is, we can see, as I pointed out to you yesterday, the front of the brain, here's the nose up here. Here is a tract, the Cingulum Tract as it's called, and it connects the front here all the way back here to the back. And here's another one here, the superior longitudinal fasciculus. It protects here all the way back. And here's one's going to the side, not going to the back here at all. And here's other ones and other ones. Now, all that white matter that I showed you yesterday is really these tracts. So it's not really something to be terribly surprised about. But when activity increases here, it also increases in synchrony back here because they're connected to each other. One's driving the other one at certain times, if you like. Now that's very interesting because there's only a finite number of these. I mean, it's not an infinite amount of things going on connected to everything in correlation. There's just one connected there to there, and another one blah, 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 and I won't go through them all. But there's a certain set of these correlations that are going on in the activity of your brain. Now let me pause for a moment and say this, that when it comes to the way in which your nervous system moves your limbs, that was a great mystery. And I think perhaps the most illuminating two periods in the whole history of that was occurred around the time of Leonardo da Vinci and Vesalius. And what they did was to show that instead of there just being this massive muscle, which is your leg, and you're just going to move it around like that, the first thing they showed was not delineating that this is the sartorius muscle or this is the gastrocnemius muscle and that kind of thing. They delineated the nerves. They showed that the massive sciatic nerve that comes out of here and that gives you all trouble with your back pain, the massive sciatic nerve comes out here and goes through the buttock, goes down there, and then it breaks up into these exquisite branches, one of which goes here, and one there, and one down there, and the femoral nerve, and one down here, and it branches into little bits. And they followed that meticulously, particularly Leonardo, meticulously. And so they realised that since the nerve was carrying the spiritus substance of Galen, since it was carrying the substance responsible for the movement of muscles, then the muscles were really, in a sense, being delineated functionally by the breaking up of the nerves. It wasn't the muscles came first, and then the nerves are hooked in. It's the branching of the nerves which showed the functionality and breakup of the muscles of the limb. I mention all that as analogous to the brain, because it's as if this kind of thing here, working out where all the nerves are going, is analogous to the situation where we have the nerves, the sciatic nerve in this case, breaking up and ending up in these different parts of your limb. And then we come along and we look at the grey matter and see which bits of grey matter, that is to say clumps of neurons, which clumps of neurons belong here, or muscle if you like, you want the analogy to be pushed further, and which clumps are here, and which... So we're breaking it up, I think, in an analogous way to what happened way back then in the 14th and 15th century, and it's extremely illuminating. We've got something to hang on to, like the geneticists, I believe, do. We've got a structure, we've got an armature. So the armature is there physically, and in addition to that, we've got activity. It's not just there structurally, it's there functionally, because we know that this particular bit here, which I keep emphasising, the cingulum, that it's connecting there, and those two areas are correlated all the time in activity. And so on with the other structures in that particular part of the brain. Well, again, you might say, so what? Well, the so what part is this. How does this impact on the question of you becoming unconscious? And it impacts in this way, that at present it would appear that as you become unconscious, as in fact you drop down from that 100% level of activity down to the 50% level of activity when you're completely out to it, that these correlations are lost. Of course, the tracks aren't lost. You don't lose whole nerves when you go to sleep and then put nerves back again when you wake up in the morning. They're still there, but the correlated activity, that is the fact that this one is taking off and driving this one up here, that in some parts of the brain, not all the parts, that is lost. Now, that is shown here in the next slide. What I'm showing you here is that we've got, it's not coming out actually, the red's not coming out there, which is some of the, don't know what's going on there. But that's a red blurb there, that's red, that's red, 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 where that black is there. Now, what that region there is the frontal region, which is very active when you're normally awake, and this is the back region, which is very active too. And the redness refers, or the blackness, refers to the extent of correlation there. So, the interesting thing is that when you go from here and you take the anaesthetic and you become unconscious to there, you'll notice that this black region is gone, virtually gone. That is, this is no longer correlated with that. It is when you're awake and it isn't when you're asleep. Now, nothing's been stripped out, I emphasise, no axons have been lost or anything like that. But clearly part of the reason why the amount of activity in the brain is dropping about 50% is because these kinds of ways in which one part of the brain is driving another part of the brain, in some cases, are being lost. And that is, as a consequence of that, you are becoming unconscious under the conditions of an anaesthetic. A very nice experiment to drive this one home is indicated here. And that is, you take an electrode, a stimulating electrode, and, well, you don't take a stimulating one, but you effectively take a stimulated electrode, and this is a normal awake person, and you stimulate that frontal part of the brain there. When you do that, you immediately stimulate this part at the back here, the part which is normally correlated with it under resting conditions. But in this case here, this is not a condition of just normally arising. This is being driven at the back by you stimulating the front. And of course, as I keep emphasising, there are axons connecting those two there. So it's natural that if you drive that, then the axons will lead to this being driven. When the person has had the anaesthetic, it won't work. You now stimulate this region here, and of course you activate the region where you're stimulating, but this is no longer activated at the back. It's become functionally disconnected, even though the structural connections there, those big nerve trunks, are of course still in place. This is someone who is unconscious. They have been anaesthetised. This is someone who is conscious. So that emphasises the fact that there seem to be these very interesting correlations going on. Now, I can give you another example of this, only this is more natural, and this is you falling asleep. So again, I'm giving you the activity being correlated at the front here with that at the back here. And then as you fall asleep, going down here, then gradually what happens is it's no longer correlated. The back is still active and it's correlated with other activities, but it's not correlated with the front. The correlations with the front are gone. So again, that 50% drop in the activity of the brain in sleep, as in anaesthesia, is showing you the results of what happens. And I'm giving that to you now in a little diagram. Here is the front of the brain, medial front, F for front. Here is the part at the back here. This is the structural and functional connection found there when you're awake. But when you fall asleep, that's gone. Not structurally, but it functionally. The synapses which are mediating that connection are turned off, and you're now unconscious. Now, you can develop this theme in many different ways. You can, for example, take someone who's caught in that terrible condition of being in the vegetative state. That is, there's someone who, for example, there are many famous cases. There was one in America called Karen Kelly, who went to a lovely party, as people do when they're 21 years of age, and took both methamphetamine as well as vodka, and got herself into a lot of trouble, ended up in the vegetative state, where, of course, quite often you need a respirator, not always, need a respirator. There's very little activity that can be recorded from the cortex at all. Now, under those conditions, you can get yourself into a lot of trouble with these kinds of phenomena, as shown here. Now, this will really throw you out, But here's the normal connection between the front and the back. That yellow line there indicates it. And in the case of the vegetative state, it's completely gone, and as is every other connection in terms of these functional connections of ongoing activity. Nothing has been recorded at all. So certainly such a person is unconscious. And what I'm suggesting to you is what's happening here is that we have these wonderful structures here which we're gradually sorting out. They are mediating these ongoing activities all the time when we're fully awake. The connections here, the synaptic connections here or there, are gradually turned off as you become unconscious, whether it's due to a general anaesthetic or whether you're going to sleep or whether it's under the conditions of the tragedy of being in the vegetative state. So, what I started out with was this diagram, which I gave you yesterday as well. Here are all the neurons, say up the front, and here are all the neurons up the back. And they're connected to each other. I gave you that big track connecting one to the other going through here. This is functionally looks like it's being turned off during the conditions of you gradually falling asleep or general anaesthetic. And it's a consequence of being turned off, you become unconscious. Now, I haven't emphasised the fact that there are a number of other such networks, if you like, which do not turn off when you go to sleep or become unconscious as a consequence of an anaesthetic. But certainly this one between the front and the back looks like it is being turned off and is a concomitant corporeal change giving you the basis of you being unconscious. I'm going to finish with my second last PowerPoint, which is showing you something which you're going to be horrified at, and that is this. Here are neurons in a group, and there over there is another set of neurons in the group, and they're connected via these long projections going, the case I've kept emphasising is the front and the back. And all I've done here is to do that diagrammatically. Here's a bunch of neurons doing all their things, and here's another bunch of neurons doing their things, and we forget about that. And we're connecting the front of the brain to the back of the brain with this lovely tract of neural axons connecting the two there. And what I'm saying to you is that if you just set that system up, you can do it quite easily mathematically. It'll rip along. It'll set up firings all the time, and this one will drive that one, and everything will be merry. And then if you gradually turn off these connections, you'll find that the activity, the correlated activity here, naturally enough drops because they're no longer very well connected, but also their intrinsic activity drops, not just the correlations, but the amount of activity there will drop about 50%. That is, it'll drop about the same amount as you see dropped according to the energy measurements I showed you in that graph as you go unconscious. As you become unconscious, these activities drop by about that amount, 50%, because the correlations are gradually dropped, one is no longer driving the other, and the whole thing settles down, and you're no longer conscious at all. The story I've taken you through here in the last two presentations is this. We started off with the idea of the ventricular theory of the corporeal. That is, that our capacities to remember, feel, perceive, and think, and all the rest of it reside in the spiritus substance found there in the three ventricles, one for memory, one for thinking, and one for emotions and sensations, for that matter. And then we came to the argument that Descartes had, that we can hook all this together if we talk about consciousness and have consciousness interacting with the vitreous substance via this wonderful arrangement of the pineal gland and the wiggles. Then the whole story was shifted, as I mentioned to you yesterday, when just about the time of Descartes' death, Willis and Christopher Wren in Oxford showed that there was no correlation between where blood flow went and where the ventricles were. That is to say, the ventricles could not have the magic psychic substance which went down nerves and controlled your muscles, because the blood vessels which carried the psychic substance from the heart, you having breathed in the ether going to the heart, as Aristotle had argued, and being turned into pneuma, and then the psychic substance, once the stuff had been pumped up into the brain, into the vitreous, and then it went out the vitreous, down the nerves, that was not a goer because the blood vessels had nothing to do with the ventricles at all. It was the cortex. Now where we're at, in these contemporary times, in the first part of the 21st century, is in fact the consciousness is dependent. You notice I say dependent because the book with Peter Hacker, Philosophical Foundation, made this distinction at length. It is not the corporeal, but the consciousness is clearly dependent on the corporeal, that is, the workings of this cortex. And where we are now is saying that that is correlated, that consciousness is correlated with the correlated activity in certain parts of the brain. And if that is lost, then we become unconscious. But I emphasise the fact that there are other parts of the brain that are undergoing correlated activity, and that is not apparently lost at all when you become unconscious. And I hope it wouldn't be, because when you become unconscious, as you know, because of the diagram I showed you, 50% of the activity of the brain is still going on. Freud would have been very happy with that result. Freud was really quite a genius. I think his greatest contributions were, one, he could be regarded as one of the two discoverers of the neuron. Before Cajal, Freud dissected out a neuron, one neuron on its own, from a crustacean, and that was an extraordinary thing to have done because it showed that a neuron was an isolated cell, that is, it wasn't something in a syncytium with everything else, connected with everything else. He did that. Secondly, he partook in some very important experiments discovering the first anaesthetic, cocaine or procaine, as we now have. Then he went astray and spent some time developing ideas about the subconscious. I think that's coming right back in again now because of that 50% that's hanging around of all that activity when you're fully unconscious and we don't know what it's doing. So in summary then, where are we with respect to Sherrington being here at Yale 100 years ago? Well, I've said that consciousness, being conscious or unconscious, something which you weren't able to do until the 19th century, depends on these sustained integrative actions of the cortex, these correlated activities, these integrated activities. Yesterday, I made some comment about transient integrative actions associated with you, say, distinguishing between letters and numbers on a screen or something like that. The concepts here compared with Sherrington's great work, which came out of his Yale lectures, and you wait till you read my book coming out of these lectures, his great work called The Integrative Action of the Nervous System, delivered as the Silman Lectures in 1904, what Sherrington had done is something which is really very remarkable. Because as I touched on yesterday, Sherrington showed that walking, locomotion like this, could be seen to be the integration of specific modular reflexes. The stretch reflex, the reflex associated with a sudden tendon jerk, which gives you that kind of action of your foot, sudden flexor action, extensor action in this case. The crossed extensor reflex, whereby you put one foot down and you lift the other foot up and you hold that against gravity. He worked out these reflexes and he put them all together and showed how you would produce locomotion, walking. And then he showed, finally, that you could get this because he took dogs and showed that their spinal cord alone could allow them to walk without the brain being involved at all. Now you might say, well, that was a wonderful piece of physiology. It was one of the two greatest pieces of physiology of the 20th century. But until Sherrington, the argument which Aristotle had put 2,300 years earlier still stood, and that is that there must be a spinal soul. There must be a soul in the spinal cord because we are able to walk around like this, and you can see other animals and their brain's not connected to their spinal cord at all, and they can also walk around like your chook in the yard and all this sort of thing. So as Aristotle had observed with lizards and other animals, including birds and chooks, they can continue on their merry way with no connections between the head and the spinal cord. So there must be a soul in the spinal cord. Now that's a very interesting kind of point because many great physiologists in the 19th century thought that was true, that there was a soul in the spine, until Sherrington. There is no logical basis for rejecting the fact that there's a soul in the spinal cord as a consequence of Sherrington's experiments. And what will be interesting to see in the next 20 years of my research is whether in fact the concept of a soul in the brain also gradually is put aside, is no longer emphasised at all, is no longer a major issue about how we have the corporeal related to the mind and consciousness, because so many of the integrative actions that we're now working on have actually come true in the ways in which I've sketched very briefly here. Thank you very much.
You can take your own questions.
Thank you. I've got this wonderful gadget now, though. Yeah.
Where does meditation, the meditative state, fall within that continuum from?
That's a terrific question. The last person who asked me that question was someone in a 3-hour dialogue at our national university, and his name was the Dalai Lama. And we actually don't have an answer to that, and it could easily be sorted out. There are difficulties, and that is, there's a lot of noise when you shove a head into one of these gadgets, and it's not easy to meditate with that kind of noise going on. A lot of work, not a lot, some work has been done with magnetic resonance, looking at grey matter changes in people who do a lot of meditation. And there are certain arguments there about the effects on the grey matter, the beneficial effects on the grey matter. But I don't know at present of any measurement of this kind. But it could be done with these energy measurements which Bob's laboratory began. They, I think, could be performed in this case.
So might you do that in the next 20 years?
Absolutely, it's on my list, absolutely. Yeah.
Do chemical mediators at the synapses play any role?
Well, you're nearly there with the key question. You're hovering around the key question. It was amazing. I had a class, at the University of Sydney before I came away, I gave this talk, and it was full of psychiatrists and neurophysiologists and all the rest of it. And I said in my talk, there's one key question here, and I hope one of them will ask. I'm not going to give it to you now. And no one asked the question, of course. At the very end, the guy asked the question. It was electrical engineer. I was very proud because that was my first degree, electrical engineering. The answer to your question, to come to the point, is that the key question, of course, is you've got the physical axon tracks there, the nerves going, and yet they become non-functional in some regions when you become unconscious. How does that happen? Now, one, I think, persuasive argument, because I put it at the beginning of this year in a paper in PLOS One, one possibility is that there are regions of the brain down here which project in to the regions of these synapses and control their function. I'll just show it to you now. Thank you so much for the question, because it gives me an excuse to Skype. So I come back to this. This is one part of the brain up the front, and this is another part of the back, we'll say. And here's the big cingulum set of trunk of axons connecting the two. But there's another part of the brain here called the basal nucleus, for argument's sake, the nucleus of minor, and it projects up on top of these other synapses. It projects there. And if this stops working, these stop working. So it needs the cooperative activity of this thing down here to keep these synapses active. If this doesn't work, then these don't look like they're working too well at all. So you've got, structurally, you've still got all those axons in place, but functionally they're not doing so well. So the question is, next, when you go to sleep, and there's a general anaesthetic or what have you, are you turning this off? And then it's no longer doing that. For the sleep argument, and I'm sorry to involve you in physiology, for the sleep argument, your circadian rhythm, where you fall asleep, I mean, my circadian rhythm's been all over the place since I came from Sydney. So you've got the circadian rhythm, which determines so much of whether you're going to be a happy person or a depressed person, depending on how much sleep you get and what have you. That circadian rhythm is, that sleep rhythm is controlled from down here in the brainstem, in the part there which has been recognised for some 50 years, and that goes to here. So the circadian rhythm during, say, natural sleep will turn this off, which in turn can turn that off. So this structural element is there, but the correlations here can no longer act, and furthermore, therefore, since there's no longer interaction between these two, the amount of activity here drops about 50%. Does that give you a hazy idea? You're blurring over. Oh, I can't see that. Yeah, don't blame me. Yeah.
So can't remember exactly when it was done, but in the last couple of years, this group of neuroscientists has declared that animals do in fact have consciousness. And so I'm curious.
Now, wait a second. That's a big package. That'll cost you $50. I think it's remaindered now, My Philosophical Foundations of Neuroscience, available at all good bookshops. Aristotle had no trouble with that question at all.
Right.
I mean, the dog runs up, you come home, it runs up down the hallway, it knows you're there, it remembers who you are. Okay, and it's time to go for a walk, and you pick up the lead and it jumps all over you. It's got memory, for goodness sake. And that's a component, you could see, I've argued that. And you can go through these. I mean, you can go through emotion. There's no big deal involved. It's not as if we're dealing with some spiritual pneuma here. It's not big deal.
I don't think there is either, and I think it's kind of laughable that it took them so
long.
No.
These aren't laughable. These are.
But so my question is, a lot of the data you're showing us is from the human brain, and so
no, a lot of it isn't. A lot is from macaque monkeys.
Okay,
things
yeah.
like that.
And I'm curious about the other, other lower animal models that we use in neuroscience, the rat, other mice.
Actually, I'm afraid there's a little anecdote there. Bertrand Russell said you've got to be very careful about talking about lower animals, because to a Holothurian, a lower animal is actually a centipede. I mean, it just depends where you are in the hierarchy, I think.
I completely agree.
Okay.
Right. So I'm curious, though, the rat brain, for instance, is the rat brain being used for?
Absolutely, and it's got all these bits and pieces in it.
Right.
These correlations.
So you think it is important for this kind of work?
What, the rat's brain important for the human brain analysis? Or?
Well, for this particular aspect, for this.
Absolutely. I mean, it's very fascinating to see these things occurring in the other species, not the lower species, the other species. Yeah.
Thank you, Max.
I haven't got my glasses on for me, so I didn't realise it was you. Otherwise, I wouldn't have asked you to answer the question. So I'm caught now.
So thank you. Thank you for these presentations. So in preparation for your book coming out, I just want to make sure I have your thesis right. So
are you talking about Spinoza?
No, not at all. I'm talking about your presentations, which is the thesis.
Oh, okay. This is my Spinoza, but go on.
Right.
Yeah.
So the earlier question about meditation and where would meditation stand in that scale that was referred to, the strength in your response really relied on the quantitative nature of that scale that you showed.
Absolutely.
So while I applaud that, I am somewhat concerned with the use of correlations in various brain states as an argument for the loss of whatever connections that you're referring to are being altered.
Yeah.
The reason being is that when you're in the awake state, there are fluctuations in your whatever imaging signal you measure.
Yeah.
Electrical,
Yeah, of course.
signal, But let's say you're in sleep or you're meditating.
Yeah.
There are fluctuations as well.
Yeah.
Right? So correlations, for the lack of a better term, is an epiphenomenon. So are you comfortable by using an epiphenomenon to diagnose and segregate different states of the brain, or would you be far more comfortable with quantitatives?
It depends. I don't want to get involved here in front of this audience with what it is an epiphenomenon of. I don't agree with you that it's necessarily an epiphenomenon. And I think I know where you're coming from. I thought you were going to ask a slightly different question, but I don't think that's necessarily an epiphenomenon. It might be, but I don't think it necessarily is because of the energy arguments at all. The question I thought you were going to put to me is a nasty one, and that is that I was a little bit, shall I say the least, that of the 26,000 papers that were published in the area that I talked to yesterday, and those of you who attended that talk yesterday might have left in a semi-dismal state about my reflections about where we're going in terms of understanding the workings of the cortex in relationship to our psychological abilities. Today's presentation has been more ebullient because I think we are in a situation where lots of interesting techniques are available. When it comes to the correlations, this depends on certain algorithms which have difficulties with them. And I won't go into the technicalities of that, but this has to be worked out. I mean, it's the n number of modes for example, in the principal in the principal element kind of algorithm, that sort of thing. These have to be cleaned up, and if it turns out that when we get stuck into it, things start to get messy, well then we're in bad shape. But right now, people are looking at that. That is, for example, the n node routine and changing the number of n from 6 or 10 up to 60 or 80, as we talked about the other day. And it's being investigated, and things haven't altogether fallen apart by any means, although there are caveats there. So I'm not going to carry on with too much ebullience, but I've certainly got myself well out of depression over these issues of how the brain works with respect to our psychological capacities. Yeah.
It has occurred to me a number of times that I was working on some problem at the time I was falling asleep.
Yeah.
And I had no clear idea of a solution.
Yeah.
And when I woke up in the morning...
It's the lower 50%.
Excuse me?
It's the first 50%. It's the one that doesn't drop when you fall asleep.
Yeah.
It's that 50%.
Thought clearly must be
Yeah,
going on.
absolutely.
While one is not
Absolutely. Well, I mentioned the fact that we've got good evidence that the memory system is going on very well indeed when you are in total sleep. So it's that 50% that is doing some extraordinary things, and we haven't got a handle on it. I don't think we've got a handle, except the memory. Yeah.
I lost a step. So at first I thought the yellow-green lines represented activity of the white matter. But now I think you're saying that it represents neurons.
I'm sorry. These are, let me be explicit, because I'm sorry to have given this to you, because it does confabulate a little bit, but at the same time, I needed to leave you in a state where correlations as a matter of this are not mysteries. We're not back into the psychic pneuma again. I wanted to keep away from that. So to be explicit, they're neurons. Okay, they're excitatory neurons, actually. They've got this little pyramid. These are inhibitory neurons down here. They're connected to each other. So this is a circuit of neurons ripping along. And there's another one there, another circuit of neurons ripping along. But here we have this region of the brain connected to that region of the brain via these things. So these are the nerves. That's that long trunk, which I showed you earlier, which is connecting one side to the other. Let me see if I can show you too. There we are. So that's that. Okay, you got that? So they are those sorts of things. So they're not neurons per se, they're the long protrusions of the neurons called the axon, connecting one to the other. Does that answer your question?
So the yellow and the blue represent...
Going back to the diagram we're going? Yeah. These represent those trunks, those long axons, yeah. These things here, that and that. Perhaps we should talk about it later, because you're looking at...
What I lost was that you seem to be appealing to what the white matter was doing.
Yeah, well, this is the white matter here.
Okay,
that's all the white matter. Yeah, thank you for putting it explicitly. That's very important. That's the white matter. You may vaguely remember from yesterday, I showed you a diagram, which I haven't got there now, which shows you the vast amount by volume of the cortex is white matter. Remember the huge amount of white underneath the little bit of grey matter on the top. Some of us have more grey than others, but it's not much compared by volume for the white matter. Yeah.
One more question, then we'll take
Yeah.
it.
So I have a question about the idea of consciousness arises from these connections.
No, wait a second. Have to $50 at all good bookshops. I didn't say that. What I'm saying is that if you lose consciousness, these things are happening.
Right.
Okay. I didn't say these things caused anything. I said that as these things drop out, okay, they are correlated with the fact that you're losing consciousness. That's a very important distinction.
So, and the example you give about the spinal cord is very important. When you cut out the spinal cord from the brain,
Yeah.
you might think that the animal is still moving. Does the spinal cord have consciousness? But I think there is a more important nervous system in the body than the spinal cord. That if we cut out completely, I think we lose consciousness, which is that in the gut.
In the gut?
In the gut, yes. That is connected to the brain.
Now, you've got to be very careful here, very careful. There is a world expert in this room on the gut and on the enteric nervous system, and that's me. That's where I did my PhD. I wrote a book on it, on the enteric nervous system, so tread carefully.
Yeah, so I'm just saying that it might fulfill the role of underlying network of neurons that if their energy drops down, our consciousness would drop down, because I can't imagine an animal with a brain only. It hasn't been described, and the spinal cord, but with no gut whatsoever.
Well, so other people have put this to me as well. In fact, the density of neurons in the enteric plexuses is higher than that in the spinal cord or in the frontal lobes. It's incredibly high. But no one I know of has correlated these kinds of networks that I'm talking about in the cortex in the gut with the loss of consciousness. The experiment has to be done. It'll be very interesting what the result was. I got out from that pretty smoothly, I thought.
Well, join me in thanking the speaker and hang out for some more questions.
Thank you.